Hi everyone, in this section we'll look at torque in more detail. An object is set into rotation by a force. Torque is a quantity that describes the ability of a force to rotate an object. The ability of a force to rotate an object depends on the magnitude of the force, the distance between the axis of rotation of the object and the point of action of the force, and the angle at which the force is applied. Torque is a quantity that accounts for all of this and then gives a measure of the ability of that force to rotate the object. It's the rotational equivalent of force. The definition of torque, tau, is RF sine theta. R is this straight line distance from the point of rotation, which is also called, or the axis of rotation, which is also called the pivot point, to the point of action of the force. It's the magnitude of a position vector that actually points along that direction. F is the magnitude of the force in newtons. And then theta here is the angle between R and F. Torque is a vector quantity. It's measured in Newton meters, and it has a sign associated with it. The conventional sign for torque is that any force that would rotate an object counterclockwise creates a positive torque, whereas any forces that would rotate the object clockwise create a negative torque. Let's look again at a diagram of different forces applied to a wrench. We've seen that forces further from the axis of rotation exert the greater torques due to the R variable in the expression for torque. Since the torque is also proportional to sine theta, the maximum torques also occur when theta equals 90 degrees. So these forces here will exert the maximum torques in the positive and the negative directions. This is when the force is perpendicular to the radial line. Now when theta equals 0, so when we're pulling parallel or anti-parallel to the radial direction, this exerts 0 torque. We can also see the sign convention here. A positive torque tries to rotate the object counterclockwise about the pivot, whereas a negative torque tries to rotate the object clockwise about the pivot. There are 3 different methods that can be used to calculate torque, so let's look at those now. The first method for calculating torque, the angle between R and F approach, is essentially what I described in the introduction. So R is the distance from the axis of rotation or the pivot point to the point where the force acts in meters. Then we have F, the force in newtons, and sine theta, where theta is the angle between R and F. And then we can plug those in and we get an expression for torque in Newton meters. And notice that we can use either angle here, theta, between R and F, or the acute angle, or the obtuse angle phi between R and F on the other side. And the reason is that sine of theta is equal to sine of 180 degrees minus theta, which is sine of phi. So either angle works here to calculate torque. And then we'll apply the sign convention as described, where counterclockwise rotation is positive and a clockwise rotation is negative. So we look at the force and imagine which way it would rotate the object. So this one is pulling the object counterclockwise, so it would create a positive torque. The second method for calculating torque is called the lever arm approach, and this method would often be useful for objects at an angle or irregular shaped objects. So let's consider this beam here with force F acting at a distance r from the axis of rotation at angle theta. The lever arm is this length here, and this is the distance that points from the axis of rotation to the line of action of the force. The line of action of a force is a line that's drawn infinitely, or it extends infinitely in both directions through the point of action of the force. Now the lever arm intersects the line of action at a 90-degree angle. So the lever arm L equals R sine theta, and you can see that from using trigonometry on this triangle here. So now using this lever arm method, we have torque equals plus or minus LF. and still using the same sign convention as before. Now notice that this really isn't a new method of calculating torque. We're always using the same definition, but it's saying that torque equals RF sine theta. So let's pull out that R sine theta and call it L. And you can think of this as the perpendicular component of R to F. So we have the perpendicular component of R times the force in this method. Okay, the third method for calculating torque is called the tangential component of the force approach. So if we look at our beam, a force acting on it or acting on any object can be split up into two components, as we've done with x and y components. But this time for angular quantities, we can think of this as a radial and a tangential component. So the radial component is parallel or anti-parallel to this radial line, and then the tangential component is perpendicular to the radial line. This method is useful because we know that only the tangential component creates the torque. Any parallel components of forces or parallel forces would cause zero torque. So the tangential component of the force is equal to F sine theta, and then the torque is given by plus or minus R F tangential, using the same sign convention for clockwise and counterclockwise rotation. Again, notice that this isn't really a new definition. This is just thinking of our torque definition in a new way. So we have RF sine theta. We can combine this and show that this is the component of the force that's perpendicular to R. So torque is equal to R times the component of F that's perpendicular to it. So RF sine theta or RF tangential. So far, we've looked at calculating torque due to one force acting on an object. When more than one force acts on an object, we can calculate the net torque. The net torque is the sum of all of the individual torques acting on an object, and this is similar to net force. So to calculate a net torque, you're going to select the pivot point or the axis of rotation, and then calculate the torque due to each force acting on the object in reference to that axis of rotation. Then we add up all of the torques, and this gives us the net torque. So far, we have treated all objects as point masses. For many irregular objects, we will need to consider forces acting at different points on the object. The force of gravity acts at the center of gravity of an object. For objects near Earth's surface in a uniform gravitational field, this point is also equal to its center of mass. In this course, we consider symmetrical objects where the center of mass is located at the geometric center. So you can place the force of gravity at the geometric center of any objects that we encounter in examples. Example 1, a student opens a 1.20 meter wide door by pushing on it with a force of 60 newtons directed perpendicular to its surface. What magnitude of torque do they apply about an axis through the hinges if the force is applied A at the center of the door, B at the edge furthest from the hinges? Okay, first we will consider the case where the force is applied at the center of the door. So I've just sketched the door here, and we're using an axis through the hinges of the door. So the force is at a distance of r equals 0.6 meters from the axis of rotation or the pivot point here. And then I'll use the RF sine theta definition of torque. So we have R is 0.6 meters, F 60 newtons, times sine of 90. The angle here is 90 degrees between the force and R. And this gives a value of 36 Newton meters. Now remember to add a sign to your torque values. So this force would pull the door counterclockwise, so it is a positive torque. All right, now in part B, this is the case where instead the force is applied at the end of the door here. So now this is a distance of 1.20 meters from the axis of rotation. So we'll have torque equals RF sine theta. It's still in the counterclockwise direction, so positive, but that's 1.20 meters times F, 60.0 newtons, and then again sine 90. So we can see this is twice the torque that we had in part A, 72 Newton meters. So this again shows that a force applied exerts a greater torque at a distance that's further away from the axis of rotation. Example 2, find the net torque on the wheel about the axis through point O and perpendicular to the page, taking A equals 10 centimeters and B equals 25 centimeters. So I've redrawn the wheel here and labeled each of the forces 1, 2, and 3. And let's calculate the torque exerted by each force and then the net torque on the wheel. So let's start with the torque exerted by force 1. If I draw a straight line from the axis of rotation to the point of action of the force, this is R, and this is equal to the radius of the outer circle, so that's B. So we have torque equals plus or minus RF sine theta. Let's assign the sign right away here. This force would pull this object clockwise, so that's going to be a negative torque, negative RF sine theta. So this is negative B, which is 25 centimeters, so 0.25 meters, times 10 newtons, and then notice that the angle between R and F is 90 degrees, so sine 90, which is equal to 1. And this gives negative 2.5 Newton meters. Now let's do the same for the torque by F2, so that was T1. The torque by force 2 here, this is also clockwise, so negative RF sine theta, and this time it's still the outer radius, so we'll have negative 0.25 meters. The force is 9 newtons. And again, if I draw in R here, we can see that this force is perpendicular to the radius. So this is still sine of 90, which gives a value of negative 2.25 Newton meters for the torque from F2. Now before I go on to F3, even though we're given the angle here in the diagram, which is 30 degrees, the angle we're interested in is the angle between R, this position vector here, and the force. And since this force is tangent to the circle, just like F1 and F2, it's still at 90 degrees to this position vector from the axis. So we'll still have sine 90 for that force. Okay, torque 3 is going to be in the opposite direction to F1 and F2. It will rotate the wheel in the counterclockwise direction, so that will be a positive torque. We'll have positive RF sine theta, which is 12 newtons, times inner radius A, which is 0.10 meters, sine 90, giving 1.2 Newton meters for the torque by F3. Now to find the net torque, I'm going to sum all the individual torques, so that will be T net equals T1 plus 2 plus 3. So that's negative 2.5 Newton meters minus 2.25 Newton meters plus 1.2 Newton meters to give a total net torque of negative 3.55 Newton meters. Example 3, calculate the torque due to the two forces and the net torque using each of the approaches demonstrated in class. Alright, so I'll start with the angle between R and F approach. We have this object with a pivot point or axis of rotation labeled at point O. So we'll use that. And then two forces, F1 and F2, each at different distances from this axis of rotation. So let's start with the torque exerted by F1. This is going to be in the clockwise direction, so that will be negative. So the torque due to F1 will be negative R1 F1 sine theta 1. I'll label each of the variables. So that will be negative the total distance from the point of rotation, which is 5 meters, times 8 newtons, sine 90, since this force is perpendicular to that axis of rotation. And this gives negative 40 Newton meters. Now looking at the torque due to F2, we can see that this would rotate the object counterclockwise, so that will be positive. Positive R2, F2, sine theta 2 is going to be 2 meters times 12 newtons, sine of 30, since that's the angle between R and F this time, and that is 12 Newton meters. So to find the net torque, we want to add both of those up. The net torque will be negative 40 Newton meters plus 12 Newton meters, which is negative 28 Newton meters. All right, I've moved this up and drawn the sketch again. So now let's do the lever arm approach. It's largely the same, especially for F1. So what we're going to do is use torque equals plus or minus FL, where L is the lever arm, which is a line that's drawn from the axis of rotation to intersect the line of action of the force at a 90-degree angle. So for F1, this is already perpendicular, so this is the line of action, and R will go straight through the object just as it did before. So that will look the same. I'll write it again. And it's still clockwise, so we'll have negative F1 L1, which will be negative 8 newtons times 5 meters, so negative 40 Newton meters. Now when I go to draw torque 2, positive F2 L2, I'm going to draw the lever arm. This is my line of action of the force all the way through the force, extending in both directions. The lever arm is here from this point of rotation to this line and intersecting at 90 degrees, that's L. And we can see that this was R2 here. So we have L2 equals R2 sine 30. So 2 meters sine 30, which is 1 meter. So then when I calculate torque 2, it's going to be 12 newtons times 1 meter, which is 12 Newton meters. So of course we get the same values as before, and if we're going to add them up to get the net torque, we would still have negative 40 Newton meters, which was our first result, plus 12 Newton meters to give negative 28 Newton meters. So both methods work, and we shouldn't see any differences in the answers. Okay, lastly, we have the tangential component of the force approach. So again, using the same axis of rotation. If we look at F1, it is perpendicular. So again, nothing really changes for the three approaches with F1. This time we're using torque equals plus or minus F tangential times R. So for torque 1, this is going to be negative F1 tangential times R1. This entire force is tangential to the motion or perpendicular to the radius. So we have negative 8 newtons times 5 meters, which is negative 40 Newton meters. Now looking at F2, this is the tangential component of the force, F2 tangential, which is opposite to this 30 degrees. It acts here, but if it helps, you can draw the component there. You could also draw it right here. This is still F2 tangential, so drawing it in either location works. And we can see that since it's opposite, we're going to have F2 tangential equals F2 sine 30. So 12 newtons sine 30, which is 6 newtons. And now plugging that into torque 2, our counterclockwise torque is going to be plus that 2 meters times 6 newtons, which gives positive 12 newton meters. So again, finding the net torque looks the same. We're adding up negative 40 plus 12 newtons, so we have the net torque is negative 28 newton meters. And so all three methods do the same here, so you can use whichever one makes the most sense to you because they are all essentially the same formula and lead to the same results. Example 4, calculate the net torque on the beam about an axis through A, O, perpendicular to the page, and B, C, perpendicular to the page. Okay, so I've drawn out the diagram again here, and I've labeled the forces 1 to 3 just starting from the left. And so for part A, we're using this axis here through point O as the pivot point, so we can imagine the rotation occurring through that point. And now if we do choose this point, notice that F1 acts at the pivot point. So R is 0. So we would have tau 1 equals R1 F1 sine theta, but any forces that act at the pivot point or the axis of rotation exert 0 torque. So that's 0. Now torque 2, this would turn the object counterclockwise, so that's going to be positive. We'll have positive R2 F2 sine theta 2. So that's positive 2 meters from point O. F2 is 25 newtons. Now I need sine of 60 degrees here. So 30 degrees is to this vertical axis, but we want the angle between R and F, which is this 60 degree angle here. So sine 60, and this gives 43.3 newton meters. Okay, now for this torque at the end, this would rotate the object clockwise, so torque 3 is going to be negative R3 F3 sine theta 3. So that's negative 4 meters times 10 newtons sine 20. So negative 13.7 newton meters. And now to find the net torque, we add up the torques due to each force, so that's 0 plus 43.3 newton meters minus 13.7 newton meters. So there's a net torque of 29.6 newton meters if point O is the axis of rotation. Okay, back to the diagram here. Now for part B, we're using point C as the axis of rotation. So right away now we can see that F2 acts at that axis of rotation, so the torque due to F2 is equal to 0. So let's look at the torque due to F1 now. If it's rotating about this point here, then F1 would pull that object counterclockwise. So torque 1 is going to be positive. Torque 1 will be R1 F1 sine theta 1. So 2 meters is the distance from the point to the force times 30 newtons sine 45, which is 42.4 newton meters. And then if we look at F3, this would pull the object clockwise, so that's going to be negative R3 F3 sine theta 3. This is also 2 meters now to that midpoint, point C. Then we have 10 newtons sine 20, which is negative 6.84 newton meters. Okay, and the net torque will be the sum of all the values, 0 plus 42.4 newton meters minus 6.84 newton meters. And that gives a net torque of 35.6 newton meters if the axis of rotation were instead to be at the midpoint of the object.